Hi there, my name is Vasu Gupta and I'm joined here with my team members Leroy Milton and Irvin Pascual to talk about our project on retinal segmentation for glaucoma diagnosis using deep learning. So without any further ado, let's get started. So first of all, let's talk about what is glaucoma. It's an eye disease which is one of the leading causes for irreversible blindness around the globe. In the early stages, the patients tend to be asymptomatic, but as the disease progresses, the visual loss also occurs as a result of it. So it becomes very essential and crucial to diagnose glaucoma in its early stages. On the screen here, we have two zoomed in images of retina of the human eye. The outer bright part is called the optic disc, and the inner bright part is called the optic cup. Now, one of the major indicators for glaucoma is the enlargement of optic cup with respect to optic disc. So as you can see on the right, on the eye without the glaucoma, the optic cup is relatively smaller than the eye with glaucoma. Therefore, to diagnose it, we need to identify how big these parts are. So we created a deep learning system where the input to the deep learning system was 2D retina images, as you can see here. And their corresponding ground truth images, like the one on the right hand side, that essentially tells what each pixel on the image belongs to. So the white corresponds to the background, the gray corresponds to the optic disc, and the black corresponds to the optic cup. Now the data for our model was gathered from Refuge, which is a challenge on ophthalmic medical image analysis. The current methods of glaucoma diagnosis include the use of optical coherence tomography, OCT in short, which is a technique to obtain a topographical map of the optical nerve head. However, the equipment used for OCT is quite expensive and it's not readily available at every eye clinic. So on the other hand, there's another technique called color fundus photography, which is a cost-effective way to take retina images, and it's also available at majority of the eye clinics. So if I quickly go back a slide, the images we have for the retina in our project were taken from color fundus photography. So another thing about glaucoma is unfamiliarity with this disease is one of the big risk factors for misdiagnosis. And an accurate diagnosis requires experts specializing in this area. So having a computerized method to detect glaucoma will not only eliminate the need of experts, but it will also save a lot of time and money at the same time. So our proposed method involves a two-step approach to segment optic disc and optic cup. The first is to identify the optic nerve head area, and the second is to perform image segmentation on the cropped version of the image. Now, Irvin, who is joined here with me, is going to take you guys through these two steps in a bit more detail. After you, Irvin.
Thanks, Vasu. So how our optic nerve head algorithm works is first a retinal image gets converted into a grayscale. After the grayscaling is applied to the image, it then goes through a blurring process which uses bilateral filtration and medium blur just to remove any unwanted noise in the image. And then the denoise image passes through a thresholding function just to segment the image into the optic nerve head and the background. And then after that, the segmented mask goes through another round of denoising just to remove any unwanted noise. After that is done, the center of the blob is calculated, in which the bounding box is placed around the center of the blob on the original image. But let's just say that there's more than one blob that results in the segmented image. We would just pick the largest one, we would just calculate the center of the blob for that one, and then we would place the bounding box on the center of the blob on the original image. After the image gets cropped via bounding box dimensions, it will pass through some random image augmentations, which in this case, rotation is only applied, but that's not the only augmentation in a random data augmentation process. It can include random brightness, contrast, gamma, rotation, RGB shifts, transposition, translation, and scaling, each with their own respective probabilities. After the image augmentations are applied, the images are then normalized just to ensure that each pixel in each color channel has similar data distribution. After the normalization process is done, our images are then fed through our architecture, which then spits out the predicted mask. So before we proceed with things, let me just discuss what exactly is a neural network. So a neural network is essentially a computational learning system that uses a network of functions just to understand and translate data input of one form into the desired output. So basically, neural networks just take in the data, they train themselves to recognize the patterns in order to predict the outputs of similar data. So neural networks are made up of layers of neurons, which can then be categorized into three main components. The first component is the input layer, which takes in our data. And this data can be viewed as each pixel of an image. So let's say your image is 20 by 20 pixels big. The number of neurons in the input layer will be 400. So the second component is the hidden layer. The hidden layer is basically the layer that performs the most computation that is required in our network. And then the last component of the neural network is the output layer. This just predicts the final output or what we want to predict. In our case, the output that we want to predict is the segmented mask of the retinal image. During the training phase of the model, the neurons in the hidden layer get activated, which leads us to an answer. So during this phase, we then calculate the error in the prediction versus the expected value. So thus, our model is corrected by the process of correction in the network called backpropagation. And this happens for the entire training data set. In the prediction process, we have the image, but we don't know the answer associated with it. So in order to find the answer, we then pass the image through our network, and the last layer of the network, which is the output layer, will predict the results that we want. So for our segmentation, we use a special type of neural network called the convolutional neural network, or a CNN. A CNN is just effectively used for image recognition and classification. So the role or purpose of a CNN is to basically reduce the images into a form which is easier to process without losing features which are critical for getting a good prediction. Our network, on the other hand, uses a specific type of CNN, which is called UNet, that is primarily used for biomedical image segmentation. The main reason why it's called UNet, well, because it's shaped like the letter U, and as the image passes through the convolutional layers of UNet, the features in each color channel get more emphasized. So Leroy will be taking us through our implementation details and the results of our project. Off to you, Leroy.
So the libraries we used, OpenCV, PyTorch, and Albumentations. OpenCV was for the optic nerve head algorithm, basically trying to get the bounding box around that as well. PyTorch is the machine learning library, so that's kind of the meat of our project. Albumentations, as Erwin discussed, is for the augmentations. We selected some of them, which were randomly chosen as well. So the training details, we did about 40 epochs. Each batch size was 4. So in each iteration that happens, there's 4 images that get processed at a time. We used Google Colab, which was really fun to kind of work together. It has 12 gigabytes of RAM on a Tesla K80. So here's some of our results. We chose to do 3 different runs, essentially. The first run was including the optical disc, or the optic disc, and the optic cup together. But you can see that it was only 72%, which is not good. We were aiming for something closer to 90%. But so we decided to break them apart. We took the optic disc and the optic cup separately, which kind of gave us a little bit better by 10%, 82.95. Yeah. So future work, architectural changes. We definitely be able to make some adjustments to try and get our accuracy higher. The other thing, hyperparameter tuning. So there's a whole bunch of different parameters that we can change in order to help increase our accuracy as well. Post-processing, including some noise removal and elliptical fitting, which would allow for better segmentation, essentially, or and the comparison of alternative models would be kind of useful using DeepLab v3 and UNet++. And also glaucoma prediction based on cup-to-disc ratio. That's kind of where we were headed with this. Once we have a greater accuracy, we'll be able to calculate the ratio to cup disc ratio in order to detect the likelihood that somebody actually has glaucoma.
Now I want to thank you for your time, and if you have any questions, feel free to put them in the comment section below, and we'll try to get back to you as soon as possible. Bye for now.